subheadings. He will come in to do the matrices section, and then it'll come back to me with the complex numbers section. Cool, so let's begin. So introduction to vectors. Let's start off with the definition of planes. So we have two main equations for planes. We have the parametric vector form, and we also have the Cartesian equation. Now let's go through the parametric vector form first. So it's given by vector x equals vector a plus lambda 1 times vector v1 plus lambda 2 times vector v2 for some real scalars, lambda 1, lambda 2. Now, vector a is the position vector of any point on the plane. This is really important. You can choose any point that lies on the plane, and that could be your vector a. And vectors v1 and v2, well, we call them the direction vectors of the plane. And, well, what does this mean? This means that they are both parallel to the plane, but they cannot be parallel to each other. Otherwise, you'll just get the span of a line, which we do not want. And also, we also have the Cartesian equation of the plane. So ax1 plus bx2 plus cx3 equals d, where a, b, c, and d are some fixed reals. And note how there's no vectors in this equation, whereas whereby we only have the components of the vector x. And the only geometrical significance about this equation is that the vector, here, I'll write it here, the vector a, b, and c is perpendicular to this plane. And we'll explain why in a question that's going to come up later. Cool. So does anyone have any questions about planes and the definition of planes? No? Cool. Let's go to a question. So find the parametric form of x1 plus 2x2 plus 5x3 equals -3. So after going through probably the last 10 1131 papers, this question always comes up, and it's probably the second most popular question that I've seen to do with vectors. So essentially, we're just converting from Cartesian equation to parametric vector form. And note how in the parametric vector form, we have two real scalars, lambda 1 and lambda 2, which means we need to introduce these two parameters when we're converting from the Cartesian equation to the parametric vector form. Now, we have three variables, x1, x2, and x3, and we can actually let any two of these be our parameters. It doesn't actually matter which two you let to be our parameters. In this case, we're going to let the variables x2 and x3 be our parameters. And I'll explain why we didn't choose x1 later. We still could have, but it's a little more inconvenient because we'll be dealing with fractions. So if we set x2 to be lambda 1, our first parameter, and variable x3 to be lambda 2, our second parameter, then we rearrange and we can get an equation for x1 in terms of the two parameters. We get -3 minus 2 lambda 1 minus 5 lambda 2. And therefore, our parametric vector form of the equation is given by vector x1, x2, x3 equals, and then let's first deal with the x1 component. Well, we said just above that it's equal to -3 minus 2 lambda 1 minus 5 lambda 2. Our x2 component, well, we let it be lambda 1, and our x3 component, well, we let it be lambda 2. And we can break this single vector into three smaller vectors. We can break it into -3, 0, 0. So that's just taking the constants from that single vector, plus lambda 1 times the coefficients of lambda 1 in the single vector, and that is -2, 1, 0. And then plus lambda 2 times, and then our vector consisting of the coefficients of lambda 2 in the single vector, that is -5, 0, 1. And of course, we have to say at the end, where lambda 1 and lambda 2, they're real scalars. So we say they are in the set of reals. Cool, so does anyone have any questions about that? Cool. Let's move on. So this is a question where we're given 3 points, A, B, and C in R3, and we're given their respective position vectors. And essentially, we have to find the parametric vector form of a plane passing through all 3 of these points. and we let the plane be pi. Now this is actually the most popular vectors question in 1131 papers, and they occasionally pop up in 1141 papers. It's a very simple question, and we'll refer back to our parametric vector form of a plane. X equals A plus lambda 1 v1 plus lambda 2 v2, where lambda 1 and lambda 2 are real scalars. Now, like I said before, vector A is the position vector of any point in the plane. Now, we're actually given 3 points here, so we can choose one of the 3 points that we were given to be our vector A. We'll let this be the point A, but you could have chosen points B and C respectively. So if we let vector A be the position vector of point A, well then we just end up with our A is equal to -2, 3, -1, simply just the position vector of point A. And now, like I said before, vectors v1 and v2, well, they're the direction vectors of the plane. And like I said, they are parallel to the plane, but they can't be parallel to each other. Now, can someone tell me one possibility for vector v1, for example? Yes?
AC.
Yeah, AC. Can someone tell me another example or another possibility? Yep.
AB.
AB? Cool. Now, there's actually 6 possibilities. We could have chosen AB, AC, BA, BC, CA, CB, because they would all be parallel to the plane. So we can easily calculate all 6 of those vectors, but in reality, we only need to choose 2 of them to be our vectors v1 and v2. So we'll, yes?
You can't choose like BC and CB.
No, sorry, yeah, you can't, because that will give us the span of a line. Yep. So we choose, in our solution, we'll choose vectors AB and AC for our v1 and v2. And now the only thing we'll have to do after calculating these 2 vectors is make sure they're not parallel, because otherwise we'd get the span of a line. So we calculate vectors AB and AC. Just recall that when we calculate vector AB, it's simply just the position vector of B minus the position vector of A. And similarly, when we calculate vector AC, it's just the position vector of C minus the position vector of A. And we get these 2 vectors. So we get 7, -3, and 5, and -3, -2, and 3. So like I said, all we have to do now is make sure that these 2 vectors aren't parallel. And once we've done that, we can just sub them into that parametric vector form. This one here. Cool. Now, clearly, these 2 vectors are not parallel because you can't write one as a scalar multiple of the other. So we know that these 2 vectors aren't parallel, and thus we can just substitute our 3 vectors into that parametric vector form equation. So we get x equals -2, 3, -1, plus lambda 1 times vector AB, which is lambda 1, 7, -3, 5, plus lambda 2 times vector AC, which is -3, -2, and 3, for some real scalars, lambda 1 and lambda 2. But similarly, you could have chosen any other 2 vectors, v1 and v2, but you have to make sure that these 2 direction vectors aren't parallel to each other, because like I said, they would span out a line instead of a plane. Does anyone have any questions about that? Okay, let's move on. So we're going to move on to lines before we do a line and plane intersection question. So our definition of the line, in Rn, the parametric vector form of a line is given by vector x equals vector A plus lambda times vector v. Now, similar to the equation of a plane, vector A just represents the position vector of any point on the line. So we can choose any point, and that could be our vector A. And also, vector v is the direction vector of a line, and that just means it's parallel to the line. So note how this equation is quite similar to the parametric vector form of a plane. The only difference is we're missing that extra lambda 2 v2 component the direction vector component. And essentially the reason for this is with the planes, we needed two real scalars to create a two-dimension figure. However, for lines, we only need one direction vector component to span out a one-dimension figure. Does anyone have any questions about the definition of a line? Cool. Let's move on to an example of it. Cool. So determine the coordinates of the point of intersection of a line given by that equation and the plane given by the Cartesian equation x1 minus 3x2 plus x3 equals 15. Well, when we're trying to find the point of intersection of two figures or two equations, we're just trying to find a solution that satisfies all of our simultaneous equations. And one method we can use to solve simultaneous equations is substitution. We have four variables here. Our four variables are x1, x2, x3, and t. And we actually also have four equations. So we have that Cartesian equation of the plane. So that's our one equation. But we also have three equations within that parametric vector form of the line. And those equations are x1 equals 1 plus t. Oh, sorry. Oh my. Sorry about that. Sorry. x1 equals 1 plus t. x2 equals 2 minus t. And x3 equals 5 plus t. Those are our three linear equations we can extract from that parametric vector form of a line. Now, like I said, substitution is a common method to solve simultaneous equations. So all we can do now is substitute those three equations into that Cartesian equation of a plane, x1 minus 3x2 plus x3 equals 15. So we substitute them over here, and we get 1 plus t minus 3 times 2 minus t plus 5 plus t is equal to 15. And we can solve for t simply because it's a linear equation in t to get t equals 3. Cool. Now we can substitute that value of t back into our three linear equations. We can get x1 equals 1 plus t, which is simply just x1 equals 4. We can get x2 equals 2 minus t, which simply becomes x2 equals minus 1. And we get x3 equals 5 plus t, which simply becomes x3 equals 8. Thus, our point of intersection is 4, negative 2, 8. Now note how I didn't just leave my answer as the vector 4, negative 2, 8, because it's asking for the point of intersection. So we must actually include that concluding statement saying that the point of intersection is the point 4, negative 2, 8. So it's just like a row vector. That just guarantees you'll get full marks for this question. Whereas if you leave it as the vector 4, negative 2, 8, there's a chance you could lose a mark for that. Does anyone have any questions with that worked example? Cool. Okay, let's move on. So we're going to move on to vector geometry. So our first definition that we'll cover is the cross product. The cross product of two vectors, vectors A and vector B, in R3 is given by that equation. And it's not something we can prove. It's unfortunately one equation that we'll simply just have to memorize. But this equation actually has quite a lot of significance. So we can quickly discuss the properties of cross product of two vectors. So the most important property is the cross product, vector A times vector B, is orthogonal to both A and B. So that sign is just the sign of perpendicularity. And this is the most important property of the cross product, and it's something that we'll be using in the next few questions. Another property, well, it's actually a very interesting property. It's the area of a parallelogram spanned by the vectors A and B is actually equal to the magnitude of the cross product of vectors A and B. I'll write that here. So the area of the parallelogram, I'll just write area of parallel. So that's the area of the parallelogram spanned by vectors A and B. So we can write it like this. That's going to be equal to the magnitude of the cross product. And the proof is quite rigorous, but you don't have to know it in the courses 1131 and 1141. However, it's an interesting property, and we might be able to apply it in certain questions. Does anyone have any questions about the properties of the cross product? No? Okay, let's move on to a worked example. So in this question, we're given 3 points, A, B, and C in R3 with their respective position vectors. Let's look at part I to begin with. Find the magnitude of vector CB. Well, this is actually quite simple. The method we'll use, we'll find vector CB by having the position vector of vector B minus the position vector of vector C. And then once we do that, all we're left with is taking the magnitude of that vector, and we're done. So, subtracting the position vector of C from the position vector of V, that gives us our vector CB, and we get -3, -9, 4. And all we have to do now is take the magnitude of that. So it's the square root of the sum of the squares of each of its components. So it'd be the square root of -3 squared plus -9 squared plus 4 squared. And that ends up becoming square root of 106. Cool. Does anyone have any questions about part I? Okay, we'll move on to part 2. Find the area of the triangle with vertices A, B, and C. Now, this could look tricky the first time you see a question like this. However, we'll use the fact that we can actually calculate the area of a parallelogram and then take half of that to get the area of the triangle. Now, I'm going to draw a diagram just about here. So say we have vectors A and vectors B. And we have the parallelogram spanned by those two vectors. Now the area of this triangle is simply just half of the area of the parallelogram because the diagonal of the parallelogram bisects its area. So if we're trying to find the area of a triangle with vertices A, B, and C, well then it would just be the area would be half of the area of the parallelogram that is spanned by the vectors AB and the vector AC. And how can we find the area of the parallelogram spanned by vectors AB and vectors AC? Well, like I said before, we can use that second property of the cross product, and we can just find the magnitude of the cross product AB times AC. That'll give us the area of the parallelogram, and we simply just halve that to find the area of the triangle with vertices A, B, and C. Cool. So this is the equation at the bottom is exactly what I just said. The area of the triangle will be half times the product of vectors AB and AC. And of course, we have to find vectors AB and AC first. So finding vector AB, well, that's just the position vector of B minus the position vector of A. And we get that to be -2, -2, 1. And vector AC is the position vector of C minus the position vector of A. That becomes 1, 7, -3. Now we'll have to use the cross product formula to find vector AB times vector AC. And I'll quickly just write that here. So two vectors cross producted together. I'm just going to rewrite the equation. That's A2B3 minus A3B2, A3B1 minus A1B3, and A1B2 minus A2B1. Now we'll use this equation for the cross product to find vector AB times vector AC. And we'll do that here. And we end up getting vector AB times vector AC is -1, -5, -12. Now once we've done that, we want to find the magnitude of that cross product. And simply we just take the square root of the sum of the squares of each of its components. That'll be the square root of -1 squared plus -5 squared plus -12 squared. And that ends up becoming square root of 170. And before we said that the area of the triangle with vertices A, B, and C is simply just half that area of that parallelogram. And therefore our area of the triangle with vertices A, B, and C is just square root of 170 all onto units squared. And make sure you include the unit squared, otherwise there's a chance you'll be losing the mark for that question. Does anyone have a question on that part? Cool. Let's move on to part 3. Part 3, hence or otherwise, find the shortest distance from the point A to the line passing through B and C. Okay, well, recall that in high school, we learnt that the area of a triangle is half times the base times the perpendicular height. I'm just going to use this space on the right side. So if we have a triangle with vertices A, B, and C, and they're asking us to find the shortest distance from the point A to the line passing through B and C, well, that's just a cheeky way of saying the perpendicular distance from A to the line, to the interval BC. Because shortest distance is simply just perpendicular distance. So we're trying to find the distance from A to the interval BC, and we'll let it be D. And recall it's the perpendicular distance. Well, we know the area of the triangle, and we also know from part I what the length of BC is, or the vector CB. And we calculated above, in part I, that the magnitude of vector CB is the square root of 106. Well, that just means that the length BC in this triangle is root 106. So we know the area of the triangle, and we know the base length BC. So all we need to find now is D, and that's the perpendicular height of the triangle. So we have the area of the triangle, which we found in part 2, root 170 all on 2, equals half times D, the perpendicular height, times the base, root 106. So we get root 170 on 2 equals root 106 on 2 times D, and we can rearrange for D to get D is equal to the square root of 85 on 53. Now, in the question, there's no variable D, so we need that extra concluding statement to say that, therefore, the shortest distance from A to the line passing through B and C is square root 85 on 53 units. And recall that you have to actually include the units, otherwise you risk losing a mark for this question. Does anyone have a question about part 3? Cool. Let's move on. Let's move on to projections. So the projection of vector A onto vector B is given by that equation. Projection equals A dot B divided by B dot P, all times the vector B. Now note that this component is actually a scalar. I know it looks like a vector, but it's a scalar. So we simply just have a scalar multiple of vector B, which means the projection of A onto B is parallel to vector B, and we should expect that. Now the length of projection is given by that equation, and we can actually quickly derive this equation. So just in case you forget it in an exam or something, you can easily derive it. So the length of the projection would simply just be the length of A dot B on B dot B times vector B. And we can distribute the absolute value sign across our two components. So that would become the magnitude of A dot B all on B dot B times the magnitude of vector B. Cool. But look at the denominator of that first component. It's vector B dot vector B, and that's simply just the magnitude of B squared. So this becomes magnitude of A dot B divided by the magnitude of B all squared times that magnitude of B. And one of the magnitude of B's cancel out from the numerator and denominator. And so we're just left with the magnitude of vector A dot vector B all divided by the magnitude of vector B. And that is the equation we have in that definition. So does anyone have any questions about deriving that equation for the length of projection A on B? No? Okay, cool. Let's move on to worked example. So this is the distance between a point and a plane. And this is probably the second most common projection question you'll see in 1131 and 1141 papers. The most popular is the distance between a point and a line. However, I feel like the distance between a point and a line questions, they require the same working as distance between a point and a plane questions. However, it's usually less steps. So I thought may as well cover the one including more steps. Also note that this comes up once every 1141 paper, just in case you do 1141. So in this question, find the shortest distance between the point 3, 2, 3 and the plane given by that parametric form equation. Now let's quickly draw a diagram. So a point on the plane is 1, 2, 4. We know from our parametric vector form equation that this first vector that doesn't contain the coefficient lambda 1 or lambda 2, that's actually a position vector of any point on the plane. And thus we know that the point 1, 2, 4 is a point that lies on that plane. So I'm just going to put the point here. So that's our point 1, 2, 4. And now we have our two direction vectors of the plane, 0, 2, -1, so this vector, and -1, 1, 3, so this vector. And they're going to span out our plane. So let's just say this is our first one. We'll say that is 0, 2, -1. And this is our second direction vector. That is -1, 1, 3. And essentially that's going to be the plane that's spanned out by vectors 0, 2, -1 and -1, 1, 3. Cool, so we have our plane drawn on the diagram. And now we're trying to find the shortest distance between the point 3, 2, 3 and that plane. So let's just draw, sorry. Oh, not this again. Okay. Sorry about that. Oh, how do I erase? Okay. Sorry about that, guys. Trying to undo.
I just command Z.
Yeah, cool. Yeah, I'll just use command Z. Cool. Thanks, Noah. Cool. So we're just going to include that point 3, 2, 3 in our diagram. 3, 2, 3. Now, let's begin by drawing the vector from the point 1, 2, 4 to the point 3, 2, 3. Oh my, that's very sus. Sorry. Okay. And we're trying to find the shortest distance from the point to the plane. So I'm going to represent that. Cool. So we're going to try to find the length d. That length d would be the perpendicular distance from the point to the plane, and therefore it would also be the shortest distance from the point to the plane. So how can we find this length d? Well, what we're going to try to do is find the projection of the vector, of this vector. I'll actually label it in green. I'll call it vector A, where vector A is from this point to this point. And we're going to find the projection of that vector onto a normal to the plane. That would give us this vector here. And thus, if we're trying to find d, all we need to do then is take the magnitude of that vector. So let's begin by finding the vector from 1, 2, 4 to 3, 2, 3. So that would be equal to, sorry, I keep pressing this button. Sorry about it. Okay. That would be 2, 0, minus 1. So that's just the position vector 3, 2, 3 minus the position vector 1, 2, 4. And now once we have that vector, I'm going to call it A, like I did in the diagram. What we need to do is find the projection of that onto the normal to the plane. Well, how do we find the normal to the plane? Well, the normal to the plane is perpendicular to both the direction vectors of the plane. And therefore, one normal to the plane would simply just be the cross product of the two direction vectors of the plane, since the cross product is orthogonal to both the direction vectors. So if we have like two direction vectors that span out the plane, then our normal vector would look something like this, where it's perpendicular to the plane. And that would simply just be the cross product of our two direction vectors. Now we can find the cross product of our two direction vectors. So that will be our first direction vector, 0, 2, minus 1, cross producted with negative 1, 1, 3, our second direction vector. And we use the formula for the cross product to get that normal is equal to 7, 1, 2. Now I've just skipped out on the calculations here. All we're doing is just using that formula for the cross product we discussed before. So we get our normal to the plane is 7, 1, 2. And like I said before, what we're trying to do is find the projection of vector A onto that normal vector, 7, 1, 2, or vector n as we called it. And we're going to take the magnitude of that to find our length d. Well, instead of finding the projection first, and then taking the magnitude of that at the end, we can simply just find the magnitude of the projection in one step using this equation, the one that we actually derived. So we're going to use that equation to find the length d in one step. And we get the length of projection. I called it A, but in my solution I wrote it as P. The length of that projection is equal to dot product of the two vectors divided by the dot product of the vector n. Sorry, not the dot product, the magnitude of vector n. And after performing those calculations, we get that the length of the projection is equal to 4 on root 6. However, the length of our projection in our diagram here is simply just d. And therefore, we found d to be equal to 4 on the square root of 6. So the shortest distance from the point 323 to the plane is 4 on root 6 units. Note how I included units. Like I said before, you risk losing a mark if you don't. And also, if you wanted to, you could rationalize the denominator to get 2 on 3 times root 6. Cool. Sorry, that was a mouthful. Does anyone have any questions about that one? Cool. Okay, let's move on. I just included one question about dot products, which we'll get to, because this occasionally pops up in 1131 and 1141 papers, even though I personally think these are the easiest types of questions. But I thought we should still cover it. So quickly, the definition of the dot product. Well, the dot product of two vectors, A and B, is just the product of its components summed together. So A1, B1 plus A2, B2, all the way up to AN, BN. And yep, anyone have any questions about that definition? It's probably the most straightforward definition. No? Okay. And let's just quickly speed through this one example. So for any vectors, A and B, show that the magnitude of A plus B all squared plus the magnitude of A minus B all squared is 2 times the magnitude of A squared plus 2 times the magnitude of B squared. And then we'll have to explain the significance of this result geometrically. So let's start with part I. What we know about the dot product, it's actually one of the only useful significances of the dot product. It's that we can write the magnitude of vector A squared is simply just the dot product of A with itself. That's really one of the only properties we use with the dot product. And using this property, we can now rewrite that vector A plus B all squared as vector A plus B dot producted with vector A plus B. And similarly, we can do that with all four of those terms in the equation. However, it's a show that question, which means we're trying to go from the left-hand side to the right-hand side. And therefore, we're going to use this property twice on the vector A plus B all squared and the vector A minus B all squared. So let's get to our solution. So recall that the magnitude of x all squared is just vector x dot producted with itself. So we begin with our left-hand side, and we rewrite it as the dot product of itself and plus the dot product of itself. Now we expand the dot product because we're allowed to do this to get this line here. Cool. And note that the 2a dot b cancels out with the minus 2a dot b. And so we're just left with 2 lots of a dot a and 2 lots of b dot b. And now we can go like the reverse of that property and write those dot products as the magnitude squared. So those become 2 times the magnitude of a squared plus 2 times the magnitude of b squared, which was simply just our right-hand side in the equation we were trying to prove. And therefore, we're done with that question. Does anyone have any questions about that part? Usually these questions are the most straightforward. There really is only one thing you can do when you see that equation you're trying to prove. You're just rewriting the magnitude squared as the dot products, and then expanding and then reconverting it back into the magnitude squared. So does anyone have any questions about that first part? Cool. Part 2, I think, is a little more interesting. So, explain the significance of this result geometrically. Well, say we draw 2 vectors. So that's our vector A. That's our vector B. Well, we can actually complete the parallelogram. And we know by our properties of vectors that the vector of this long diagonal, well, that is simply just A plus B. And the vector for the shorter diagonal, say that vertex to the opposite vertex, we know that's vector A minus vector B. And now let's look at the result that we just proved. We said that the magnitude of A plus B squared plus the magnitude of A minus B squared is 2 times the magnitude of A squared plus 2 times the magnitude of B squared. Well, let's look at that left-hand side first. So we have the magnitude of A plus B squared. Well, that's simply just the magnitude of that longer diagonal squared plus the magnitude of A minus B squared. Well, that's simply just the magnitude of that shorter diagonal squared. And then let's look at the right-hand side. We have 2 lots of magnitude of vector A squared. Well, that's 2 lots of the length of this side squared, or otherwise, it's actually the length of this side squared plus the length of this side squared. And then we have plus 2 lots of magnitude of B squared. Well, that's 2 lots of this side squared. However, we can just say that it's 1 lot of this side squared plus 1 lot of this side squared, since opposite sides in the parallelogram are equal. And thus, explain the significance of this result geometrically. Well, if we consider the parallelogram spanned by the vectors A and B, then the result suggests that the sum of the squares of a parallelogram's diagonals equals the sum of the squares of the parallelogram's sides. Does anyone have any questions about that? Cool. Yep, I think that's it for vectors. I'll now pass it on to Noah so he can teach matrices, and then I'll come back with complex numbers at the end.
Sweet.
Cool.
Sweet. Hi guys, I'm Noah. I'm going to be taking over matrices, systems of equations, determinants, simplifying matrix stuff, and some other stuff as well. So let's just get started with that, I think. Let me just get used to this. Awesome. So we'll start off with an easy one, just multiplying two matrices, working out like how the dimensions of matrices matter and like why they're important. To be honest, looking at this question, you're probably thinking I could just chuck this into symbolab.com, which you could. But I think it's important to know how matrices are multiplied because, you know, you're learning math because, yeah, one, you have to study for a test, but two, there's actually real world applications where multiplying matrices together are important. So treat this as a warm-up question. I do appreciate the fact that the exam is more or less open book, so you probably could chuck this into symbolab.com, but why not just solve it now? Okay. So the first part is we want to evaluate PQ transpose. Transpose basically just means whatever were rows become columns, whatever were columns become rows. So PQ transpose, what we want to try to do is essentially take matrix P, which was 1, 3, 2, -1, 1, 4, and we want to multiply this with Q transpose. So this row vector now becomes a column vector, so 1, -1, 1, and then this row vector becomes a column vector here. Okay. What's the dimension of this new matrix? One of you guys. So what's the dimension of our answer matrix? Like what is it, a 3x3 or a 2x2? Literally just someone scream it out.
2x2.
Good. Okay, let's find out why. So this here, we have 2 rows by 3 columns, so this is a 2x3. 3 rows, 2 columns, right? So if the columns in matrix 1 match the rows in matrix 2, you're good to go. You're allowed to multiply them. That's fine. And then the outside part gives you the dimension of your new matrix, like that. Okay, so we know we're going to get some sort of 2x2 matrix where we're going to plop some numbers in here somewhere, you know. Okay, now how do I find row 1, column 1? You simply just dot the first row with the first column. So if we evaluate that dot product, that's going to be 1, 2, 1, the first row in matrix 1, dotted with the second column 1 in matrix 2, so 1, -1, 1. Doing a dot product, that's going to be 1 times 1, which is 1, plus 2 times -1, which is -2, plus 1, which is just 0. So that part there is going to be 0. So that part there will be 0. Okay. If we want row 1, column 2, you just dot row 1 with column 2. And so what we get is 1 times 2, which is 2, plus 2 times 5, which is 10, plus 1 times 0, which is 0, and you get 12 there. So that element's going to be 12. Okay, row 2, column 1, so we'll row 2 dotted with column 1. That's just going to be 3 times 1 plus -1 times -1, which is just +1, plus 4 times 1, which is just 4. So that part is going to be 8. Right? Okay. And then this one here, row 2 dotted with column 2 will give us entry 2, 2 in our matrix. So that's going to be 3 times 2, which is 6, plus -1 times 5, which is -5, plus 4 times 0, which is, yeah, so that's just going to be 1. So 0, and then that whole thing's just 1. So 1. And so that's how you multiply matrices. Keep in mind, you might have to deal with like higher dimensional matrices, but the same process follows. Okay, very nice. Evaluate the size of P transpose Q. So what you might notice is that P was a 2x3 matrix. So P transpose, if P was a 2x3, then P transpose has to be a 3 times 2. Okay. And then if we find the Q matrix, what was Q? Q was a 2x3, so that's going to be a 2x3. Again, if these match, so if column dimension in matrix 1 matches row dimension in matrix 2, you're allowed to multiply them. these give you the dimension of your new matrix, so we get a 3 by 3 matrix. And then you would calculate the matrix using just like the row column dot products and stuff, like we did in the first example. Okay, does the matrix PQ exist, and explain why? Does it exist? Hands up if it exists. Good. It doesn't exist. So, does the matrix PQ exist? Well, what is P? P is some sort of 2 by 3. So, P. Sorry, this is abhorrent notation, but hopefully you guys get the point. Q is also a 2 by 3. What's the rule with matrices? These have to match. They don't match. You can't multiply them. Therefore, you can't multiply them. So PQ does not exist. Cool. And there's everything summarized. All right. We now move on to systems of equations. So, you know, in high school, you dealt with two variables, like solve for like x and y if you're given two equations. We can generalize this to any amount of variables pretty easily. Just a few facts that's probably worth knowing. If you've got some sort of matrix where you've got all of your entries on one, and then you've got like your augmented matrix with your things to the right-hand side of the equals on the other, a few properties that you can sort of take away from this, which we'll go through in the example. I mean, here it is. So no solution if only the right-hand side is a leading column. What's a leading column? We'll go through that. And so I think while it's good to actually look at this, why don't we actually just do an example and kind of get it through there? Okay. All right. Cool. So here's a question taken from a 1141 exam. So, you know, pretty difficult, but like if you get the main ideas, you'll see it's actually not that bad. All right. So for some values of the real parameters A, B, C, and D, that curve passes through those points. Explain why the following equations can be used to determine the values of A, B, and C for which the curve passes through the points. Okay. So here, this just essentially acts as your x coordinate. This just essentially acts as your y coordinate. So why don't we sub 1, 1 here? So that's going to be A times 1 squared plus B times 1 squared plus C times 1 plus D times 1 is equal to 1. And that's pretty much it, right? That's just A plus B plus C plus D, which is equal to 1. So that's what happens if you sub in the first point. Cool. If you sub in the second point, why don't we make this guy xy now? And wherever I see x, I'm just going to sub in 2. Wherever I see y, I'm just going to sub in 3. So what's this going to be? This is going to be A times 2 squared plus B times 3 squared plus C times 2 plus D times 3. We know that that's equal to 1. And so what you get there is exactly that. So 4A plus 9B plus 2C plus D is equal to 1. And you can do that with, I encourage you to sub in 0, 1 just as an exercise. But what you'll see is that you get that last one. So I think it's actually worth noting. You should probably put 0A plus 1B plus 0C. That's quite important because when you're constructing your augmented matrix, you do need the zeros there. You can't just like leave them blank. Hopefully you guys knew that. But yeah. So that's, you kind of do want to put your zeros there just so that you, when you put in your augmented matrix that you can then row reduce, you at least, you know, you have something to work off. Okay. So that was that. So what happens is you just derive these equations, going on forward, make sure your augmented matrix, when you eventually put this into a matrix, don't put your variables in the matrix, just put the coefficients. So this is like 1A plus 1B plus 1C plus 1D is equal to 1. Don't include letters in your augmented matrix, just the coefficients. Cool. So what was question 2? Are there 0, 1, or infinitely many curves of the form this which pass through the point A, B, and C? So we've got our equations here. What this is essentially saying is just solve the system, right? So I'll save you the row operations because if I make one mistake in the row operations, the whole question's wrong. Like there's no chance of recovering. So I think it's good to just explain how the row operations work and then at least like here it is. I'd recommend maybe taking a photo, or you guys can do it while I'm speaking if you want, but it might be a bit tedious and boring. But here's how it goes. So ideally, we want to get this into a form known as row echelon form, where essentially, you have like a non-zero element here, then your next non-zero element is like slided 1 over, and then your next non-zero element is like at least like 1 over that. So you want like your leading element to be like pushed across each row you go in. That's what we ultimately want to get to. How do we do that? We apply row operations. So what you want to say is like new row I is equal to old row I minus some sort of number like C times another row, which we'll just call row J, right? And so that's what we're doing here. We want to find a way to make this guy 0. So we want to use this leading element to kill off this 4. And how do we do that? We'll say that new row 2 is equal to old row 2 minus 4 row 1. So if we just do it, so new row 2 is equal to old row 2, which was 4, minus 4 times row 1, that's 0. And that's where that 0 comes from. And what I encourage you to do is just apply this element wise. So, do row 2 minus 4 row 1 here. You'll get that 1. Do row 2 minus 4 row 1 here, and you'll get the next element. And then, you'll get these. And then you do, row 2 minus 4 row 1 here, and so on. And so what you get is you get this new augmented matrix, and you simply just kind of disregard the other one. This is the one that you're working with from now on. Okay. Now, what you kind of saw from that is that it's easy to kill off elements when the number below is bigger. So, I mean, you can row reduce from here. That's fine. But what you could do is you could swap these rows over so that you could use the smaller element to kill off the bigger one to eventually get in a row echelon form. So what we're going to do is we're going to swap row 2 and row 3 just because we can. You're allowed to swap rows at any time. And so what you get there, this notation really just means swap row 2 and row 3. And so what you get is this thing. Cool. We're almost in the row echelon form. We need to make this 0 in order for it to be in the row echelon form. And what we're going to do is we're going to use the guy above it to kill off that. And the way in which we're going to do that is by saying new row 3 is equal to old row 3 minus 5 times whatever row 2 was. So if you look here, we're only adjusting row 3. So row 1 and row 2 remain the same. Row 3 gets changed according to that calculation. Okay. All right. So, I mean, great. We know how to row reduce, but... Oh, no, that's all I asked. So use Gaussian elimination to solve the system of linear equations in part 1. So that's how we do it. Now, let's actually solve the system. So if we solve the system, how do we do this? We're now in the row echelon form, so we can do something called back substitution. And what we do is we say, well, we're in the row echelon form, so we say, okay, well, this is a leading column. This is a leading element, sorry, and this is a leading element, right? That means we have a leading column here, a leading column here, and a leading column here, and this is a non-leading column. Okay. Now, if we want to solve the system, we let the non-leading column equal some sort of free-flying parameter. So why don't we say let d equal to some sort of parameter lambda, okay? And so what we get now is the following. Cool. All right. So let me just scroll up a bit. Awesome. Okay. So we let d equal to lambda. So why don't we back substitute? So go from our bottom row and work up. So what we say is that 0a, so 0a plus 0b plus minus 2c, so minus 2c minus 6d, but d's lambda, we're going to set that equal to negative 8. Let's solve for c and not for lambda. So if we solve for c, what do we get? So we get 2c is equal to, so take that to the other side, we get 8 minus 6 lambda, which means that c is equal to 4 minus 3 lambda. Okay, great. Cool. Now we're going to go the row above. So now we're going to back substitute this row. So we're going to say 0a plus 1b, right? Now b is just, so plus b, plus 0c, so we don't have to worry about that, plus 1d, so that's just going to be lambda, is equal to 1. And so what we get here is that b has to then be 1 minus lambda. Cool. And let me just actually underline these, so those are quite important. Okay, now we're going to go for the top row, and we're going to say 1a, so 1a plus 1b, but what is b? b is 1 minus lambda, plus 1c, so that's going to be plus 4 minus 3 lambda, plus 1d, d is just lambda, and that's going to be equal to 1. Okay. Collecting stuff, well, what we get is a. Now, 1 plus 4 is 5, so plus 5, minus lambda, minus 3 lambda, plus lambda is minus 3 lambda. That's going to be equal to 1. And then we can just simplify, so a is equal to, well, what is that? So negative 4 plus 3 lambda. Okay. So what we note here is that our vector of solutions, we've solved for a, b, c, and d. So what we can say is that therefore a, b, c, d is equal to some sort of point plus lambda times some sort of other point. And let's just say that lambda is a real number, so lambda is an element of R. Okay, so a is minus 4 plus 3 lambda. B is 1 minus 1 lambda. C is 4 minus 3 lambda. And D is 0 plus 1 lambda, right? Just lambda. Okay. Cool. So that's essentially solving the system. Yeah. So that's solving the system. Are there 0, 1, or infinitely many curves of the form this, which pass through the points aforementioned up here? Now, since there's a non-leading element, so we saw from the echelon form that we have a leading column because there was a leading element there. We have another leading column because there was a leading element there. We had another one here, but there was an X in which it wasn't a leading column. And as soon as you see a non-leading column, so like an X there, there's going to be infinitely many solutions. So the answer to that is that there are infinitely many curves. Cool. All right. So I guess that was 2. 3 is infinitely many solutions, simply because one of the columns were non-leading. And then part 4 is asking us to find a parabola of the form this, which passes through A, B, and C. Yeah. So what we do is we say, well, here's what we know. We know that A, B, C, and D is equal to this thing here, right? So minus 4, 1, 4, 0 plus lambda times 3, negative 1, negative 3, 1. Right? There's lots of different curves that can pass through any of these points. But why don't we just find a curve? So why don't we just let lambda equal some sort of arbitrary value? Set lambda equal to 1. Okay. So what do we get? Well, what do we get here? We get the following. So if we look here, lambda is equal to 1. I might have screwed this up quickly. 0 plus 4 lambda. I think I've made a mistake. 4, 1, 4. Okay. I'm going to come back to that. I think I got something different in my notes. But what you're going to see here is that A, B, C, D. Okay, so let me just have a look here quickly. Give me a minute. Okay. So what I just wrote something here. Let me actually just So here's what I got, and then I'll try to explain it later if I figure out what I did. But yeah, sorry in advance. So what I got here is I got A, B, C. Just in my notes here, I said was equal to -414, so that was all good. Plus lambda times 3, -1, -3. So that part was all okay. Let lambda equal to 1, and so what we get is A, B, C is equal to, just let lambda equal to 1, add the two vectors, and you get -1, 0, 1. And what you can do now is that you can sub in, wherever you see A, you can sub in this. Wherever you see B, you can sub in this. Wherever you see C, you can sub in this. Oh, and wherever you see D, you can just sub in 0, right? Okay, so that's what the mistake was. But what you essentially get is your curve then becomes of the form this, right? So A times x squared plus b times y squared plus c times x plus d times y. So what we're going to get is the curve. If you scroll up, you just sub in A, B, and C. And then D as well, right? And so what happens is once you sub that in, rearrange to make y the subjects, right? So you're going to get y, 1y here. Rearrange to make y the subject, and you'll see that you'll get a parabola in terms of x. I do apologize for that. I must have made a mistake somewhere up here, but yeah. Anyway. Okay. But I encourage you to actually look through the slides because it was, you know, pretty clearly laid out. You can like work backwards and just kind of see what happened there. But I think as minuscule as it was, you'll see that as you sub in the numbers, you know, things will be okay. Okay. So. Cool. All right. Oh, and this is a very common exam question. So a lot of the time you'll be given like some maple code and they'll say, okay, here's some like matrix in terms of like M or something. And they'll say, okay, where is there no solution? Where are there like infinitely many solutions? And when are there, when's there just like a unique solution? So you're given some maple output here and we have to work out, okay, when is there going to be no solution? When is there going to be infinitely many and so on? Okay. All right. So if we look here, that's really what it is. That's kind of what they're alluding to with this code over here, right? Just think of the augmented matrix and think of that right-hand side as like the stuff to the right of equals. Now, if you look at this last line, it would be a massive problem if we had like 0x plus 0y plus 0z is equal to like something that's not 0, right? Let's just say C for like some sort of non-zero C. Like that would be a massive problem, right? Like 0 is equal to like 3. Now, how does that problem arise? That problem arises when, well, that problem happens when this part's 0, right? So 2m plus 3 is equal to 0, which means that m is equal to -3 on 2. So that's when the system would have no solutions, right? Because you have 0x, 0y, 0z is equal to something that's non-zero, right? You'll see you'll get like non-zero there. So, okay. And that's what you're seeing there. Okay. Now, the system has infinitely many solutions when m is equal to 1. If you sub in m equals to 1, that term's going to cancel, that term's going to cancel, and that term's going to cancel, and you're going to get a row full of zeros. And when you look at which element, which are your like leading and non-leading columns, you're going to see that you're going to get a non-leading column. And so that's one way in which you can get infinitely many solutions. Okay, so that's what they kind of tell you. The system has infinitely many solutions when m equals 1. For which other real values does m have infinitely many solutions? Well, let's just jump back up to here, and let's see what happens if these are all like zeros, right? Because in that case, you would get like a row full of zeros. You'd have a non-leading column, which you'd give to a parameter, and then in that case, there'd be like infinitely many solutions as well to that. And so that's what you're seeing here. So if we let m equal to a half, this row is going to be 0. That row is going to be 0 there, 0 there, and I believe that will also be, I'm not sure what that will be. I have to put in my calculator. But if you sub in m equals to a half, what you're going to see there is that if you then look at the structure of the matrix and you look at which columns are leading and which aren't, you're going to get a situation in which one of the columns don't lead. So that would give you infinitely many solutions as well. And so what we can say is that there's also a situation in which you have infinitely many solutions. Sorry, here, when m is equal to a half as well. And I encourage you just in matrix 3 to sub in m equals a half, especially in this bottom row, just to verify that. But I think just to do all the substitutions, given that we are on a time constraint, you know, I think it'd be best just to move on. Okay. Now, for which values of m, if any, does the system have a unique solution? Well, we've covered all the ones where there's no solution. We've covered the ones where there's infinitely many, so unique's just going to be like the rest of them. So basically what we want to say there is we've covered all the cases where there's no solution, all the cases where there's infinitely many, and then all the cases where there's unique. The unique ones will just simply be like everything that's not what we just found. So basically any number that's not like infinitely many, none. Okay. So that's unique because we've covered the previous two cases, so we can just say everything that was not the previous two cases. So for m equals 1, so they're telling you sub in m equals 1, the system has solution of the form vector x is equal to vector a plus some sort of scalar times vector v. So we want to find what happens there. If you let m equals 1, if you just kind of go up here, so wherever you see m, just chuck in 1. So you're going to get a situation in which you get a matrix that looks like this, right? Just sub in m equals 1 into that matrix 3. You're going to get something that looks like that. And you'll notice that this isn't actually in row echelon form yet. So we have to convert it into row echelon form. You could just swap row 3 and row 2, and that way like the number of zeros will increase as you go down a row. And what we see here is that if we back substitute, we're saying negative 1x2, so that's really negative 1x2 plus 2 times x3 is equal to 1. So that's one option. And then if we go to the top row, we're going to see that 1x1 plus 1x2 plus 1x3 is equal to negative 1. And that's what you see in this row here. Okay. And bold x is just a vector with all of like your mini x's in it. So that's just going to be your x1, x2, x3. And so what we can do is we can say, well, here it is, right? So what happens is if you solve for x2, sorry, what you're going to see here, if you solve for x2 and x1, making them the subject, what you can see is that you can really represent x1 as this. So x1 is going to be equal to negative 3 lambda. X2 is equal to negative 1 plus 2 lambda. And I'm just writing it like that so that you can eventually express it as that. And then x3 is going to be equal to lambda, right? 0 plus 1 lambda, but that's just really lambda. Because we had a non-leading column in the echelon form, so you give the x3 variable to a parameter called lambda. So that's how we derive lambda. Now, we had to break it up into two vectors, one with like no lambdas involved at all, and then one where you're multiplying by a lambda scalar. And so what we can do is we can break up these three into this. And if you're wondering how that's done, just think of it like this. So x1 is equal to 0 plus negative 3 times lambda. You can sort of read off like each individual row. And then you can do the same, like you can do the same here with each individual row. And so what we get is we get something of the form a plus lambda v. So quite clearly, this is like the a bit, and this is like lambda v. So a is that vector there, and v is just whatever's attached to the lambda. Okay. Yeah. Okay. Now, calculating the determinant of a 3x3 matrix is probably best done but just by memorizing this formula. There's all sorts of complicated ways in which you can do it. There's like, I think they do this like code. Sometimes people do like that sort of thing. you know, you can do that, and that's all well and good. What you might want to do is, just for convenience, just remember it as this, really. So you can remember it as that long expression where, you know, these are all your elements, and you're finding the determinant of this big 3x3 matrix. So that's how you do it. Now, an important property of a determinant is that, assuming that this is like some sort of row vector, so that's going to be some sort of row vector called bold A, that's going to be bold B, and bold C, we have this thing called the scalar triple product, where if you do A dotted with B cross C, you get the special quantity called the scalar triple product. So if they say, you know, find the scalar triple product of capital A, what you would do is you'd do lowercase a dotted with B cross C. And the reason why this works is because a vector crossed with a vector. So if you take a vector and you do the cross product with another vector, you get a vector. And then if you dot that with a vector dot product with a vector is a scalar. So you get a scalar answer. It's also known as a scalar triple product. Okay, so that's quite important. Here are some properties of determinants, which they might sometimes ask you. So they'll say like, oh, and another thing with determinants, it essentially determines whether a matrix is invertible or not. That's a really important one. So if they say like, is this matrix invertible? Just look at its determinant. And if its determinant is 0, then you have a non-invertible matrix. If it's non-zero, then you have a invertible matrix. And that's sort of that. And when you have a situation in which the matrix is non-invertible, a lot of times you're going to get an infinite number of solutions or no solutions. I guess an application of this is you'll see in some second year courses. There's a course MATH1131 or 2931 when you're like looking at linear models, and like if two vectors are like perfectly collinear to each other, you can't actually really build like your linear model with like all your parameters. So that's a topic for another time, but there is like real world application to this. But just for now, note that if the determinant is 0, you have a non-invertible matrix. If you have a non-zero determinant, you have a invertible matrix. Cool. So that was kind of point 2, what I was talking about there. So invertible if and only if det A is not 0. Now, another property that gets used quite a lot in exams is that the determinant of the product is equal to the individual products of the determinants. So you can like break them. Det product is just like the individual debts, like kind of smushed together. And then this one here. So if a row or a column, that's what people often fail to note. It can be a column as well. But if a row or column of A is multiplied by a scalar, then the value of det A is multiplied by that same scalar. And so what happens is, if the matrix B is obtained from the matrix A by multiplying a row or column of A by the scalar lambda, then det B is equal to lambda det A. The best way to illustrate that would probably be like conjuring up like an example or something. It is quite hard to explain via words, but we'll just kind of go with that for now. But let's actually do a question in which we can kind of use the theory of determinants and see how we can eventually solve these things. All right. Cool. Nice. Awesome. Okay. So we have a complex matrix here in which some of the elements are like complex, like they have like eyes and stuff. And we want to find A inverse. So fortunately, finding the inverse of a 2x2 matrix isn't that bad. It's quite troublesome when you get to 3x3 matrices or worse, 4x4. But they really won't make you invert anything above like a 3x3 in an exam. And a 2x2, inverting that's pretty simple. So I think we'll just get started with that. So we know that A was this matrix here. So I'll just rewrite it because I'm eventually going to like scroll down. So 2, 1 plus I, and alpha, like that. Now, the way in which you solve for A inverse is not actually that bad. So what you're going to say is that if we want to find A inverse, well, does anyone know the formula for 2x2 inverses? Okay, I'm sure you do, but here it is anyway. So what you do essentially is, well, if we want to find A inverse, all that we have to do is use the special formula. So we take 1 over whatever the determinant of A is. And what we do is, so you take 1 over the determinant of A, you'll clearly see there that if det A is 0, you're going to get 1 over 0, which is problematic, and that will essentially tell you, that kind of justifies why your matrix isn't invertible if the determinant is 0. But if you kind of look there, what we do is the following. So what we do is we take this 1 over det A, and we swap these elements like that, so that's going to be like that. Swap them over, and then take the negatives of both of these. So minus I, minus 1, minus I. Right, just taking the negatives of both. Okay. So we want to find the inverse. To find the inverse, we probably have to find what this guy is. And so what we say is that the determinant of A is equal to, okay, what's the determinant of A? Anybody would like to input? And just have a crack. Like, honestly, who cares if it's wrong? Anyone? Okay, I'll do it. So what you do is you do, if this is like A, B, C, and D in your matrix, you do AD minus BC. So AD, so that's going to be 2 alpha minus BC. So minus I times 1 plus I. And that's going to be equal to 2 alpha minus I squared. What's I squared? Because remember, I is complex. So I squared is -1. So negative of that is just going to be positive. So that's going to be equal to 2 alpha minus I plus 1, right? Because that's just 1. Minus 1. Okay. So what we get here is 1 over 2 alpha plus I minus I plus 1. And we kind of bang this matrix over here like that. Minus 1 minus I and minus I. And that's pretty much it. I mean, you could, if you want, like multiply the scalar to each element. I probably wouldn't do that. It's not in your best interest to do that. But yeah, so that's what you get. That's all good. Okay. Awesome. That's how you invert a 2 by 2 matrix. Okay. Now, what do we want to find here? What we want to say is find all values for A, which is complex, for which determinant of A squared is -1. Okay. So what we know is that the question told us that the determinant of A squared is equal to -1. Okay, so that's what the question told us. That's what we're working off. We want to somehow find some sort of alpha, which is complex, in which this is true. Well, how do we do that? You might want to note how A squared is really just A times A. So we could probably write this as det A is equal to -1. Because you can do that. Because if you look up here, the determinant of the product is the individual products of the determinants. So this thing really, that was like det AA, which we then decomposed into this quantity here. Okay. Now that's a scalar, right? That's a scalar. So what we can say is that det A all squared is equal to -1, right? We could probably just sub in whatever det A is, right? So why don't we sub in whatever det A is? Because we have a value for it. That's what det A is. So what we can say is 2 alpha minus I plus 1 all squared is equal to -1. Okay, how do we undo squareds? You can just square root. So square rooting both sides, we get 2 alpha minus I plus 1 is equal to, well, whenever you're square rooting, you have a plus or minus case. Square root of -1. Square root of -1. Anyone? I. Good. So that's just really going to be plus or minus I. Okay. So what we can say is just rearranging from here on in. So 2 alpha is equal to plus or minus I plus I minus 1, right? Take the I, no, minus 1, yep. And then what we can say is, well, alpha is equal to, we have two possibilities, right? So either plus or minus, so it's plus or minus I plus I minus 1 over 2. And let's just consider the positive case. So alpha is going to be equal to positive I plus I minus 1 over 2. So that's going to be 2 lots of I minus 1 over 2. That's complex. And then what we have is, yep, so that's all well and good, just double checking. And then this one here, the minus case, so we do minus I plus I minus 1. That's just minus 1 over 2. And keep in mind, minus 1 over 2. And keep in mind that minus 1 over 2 is still complex. It's just minus 1 over 2 plus 0i, right? The 0, it's 0i, so it's still complex. So what I mean by that is like you have real numbers and then you have like complex numbers where reals are still subsets of like complexes, but not the other way around. So, you know, real numbers are still complex in that sort of sense. It's just 0i, like the part after. Okay. Cool. So there you go. So that's find all alpha. That's pretty much it. So the main thing there was just noting the determinant property in which you could really express this det A squared as det A, which in fact becomes det A whole thing squared. And then it's just a bit of algebra bashing from that point on. Okay. And that's what you see here. Cool. Nice. All right. Now, here's another question involving matrices where there's a few properties that stand out, but just for now, we'll go through just some simple ones and apply to this question. I might actually do this question a slightly longer way. There's a way to do it in like 1 or 2 lines, but it might be worth just taking some time just to explore some of these interesting properties and see if we can find like a nice like 3 or 4 line solution, which might be a little bit slow, but it kind of teaches some of the properties at the same time. Yeah. All right. So, sorry. All right. Now, an important thing to note here is that if you're, let's just start off with this one. If you're taking the inverse of an entire product, so you've got like 2 matrices smushed together, or maybe 3 or 4, and you want to take the inverse of the whole thing, what that is that if you take like AB, a product, and you invert it, that's just going to be the reverse product of the inverses. So that's going to be B inverse, A inverse. You reverse it and then inverse each one. And the same thing with transposers. So AB, all transposed, is going to be reverse producted and then transpose each matrix like that. Okay. So why do we do that? So if we do that, well, what do we get? So, well, what do we get here? So this one becomes reverse product, right? So that's going to be A inverse, A transpose inverse, like that. Right, because you just reverse product, so that one, and then A transpose inverse, like that. And then what we're going to do is we're going to apply this transpose thing, which is essentially the same, but instead of inverse, you just transpose. So this is going to be A transpose, and then this one's going to be A transpose transpose. Okay. Nice. Now this becomes A inverse times A transpose inverse, like that. Now we times it by A transpose, which is that. And then this one here, what's A transpose transpose? Anybody have an answer for that? It's just A, right? Because you transpose it and then you undo it straight away. So you just get back to where you started. So that's just going to be A. Okay. Now, a matrix inversed times by the same exact matrix, not inversed, just becomes the identity, the same way like 1 over 4 times like 4 over 1 just cancels to like 1. So this really just becomes A inverse times the identity times by A. The identity, right, like 2 times 1, 2, it's very much the same thing. So you could really write this as A inverse of A. And again, a matrix inversed times by that same matrix, not inversed, just gives you the identity. So that whole thing ended up simplifying to the identity. A slightly quicker way to do this would be to leave this guy. So you could, alternative solution, you could leave this guy, so A transpose A inverse, and then you could just fiddle with this one. So that would be A transpose, which is just A. Inverse, original, cancels, you get I. But yeah, I think this one is good because it just shows a long way. Cool. And the last question, this is just a determinant question. Not too hard. This is from Milan Paho's notes, by the way. Amazing teacher. I don't know if you guys had the privilege of having him as a teacher, but wonderful teacher. This was one of his examples, so I thought I'd just take it because it's good. It shows some interesting properties. So suppose that the determinant of this matrix here is 4. We want to find the determinant of this new matrix here. So what we know just from this part alone is that how do we find the determinant of this matrix? You do AD minus BC, and we know that that's 4. Right, that's just what this part told us. Find the determinant of this matrix. Well, how do you do that? Very much the same. So determinant of this new matrix, which we'll call 2A, 200B, C, 100D, that's just going to be AD, so 2A, right? So that element there times this element there, minus 200B times by C. We can write this as 200 AD minus 200 BC. Taking out a 200, you're going to see that you eventually, inside the brackets, get AD minus BC. And we know that AD minus BC is 4, so 200 times 4 is 800. And that's how we calculate determinants like that. Amazing. So that's pretty much it. Not a hard one, but just interesting to note. I know this was like kind of scary, but if you use what you were given from this original one, then it actually becomes very simple because this is an expression that you can just sub in, most notably 4. So that's pretty much it. If you guys had any questions, you can bring it out now or like after, like in person. Otherwise, I do apologize for making a small mistake. Which one was it? I think it was, it's probably this one, wasn't it? Yeah, I think it was this one. But I did write the solution over here so that, you can just kind of see straight up that it ends up working out. All right. And that will cover it for like all the matrix stuff. I'll let Michael continue with complex numbers, which will pretty much finish it off because that covers more or less the entire 1A algebra part. So I'll pass it on to Michael now, but thanks for listening if you're online, and yeah, I'll pass it on now. Sick. Okay. Thanks.
Hi everyone. We're moving on to the complex numbers subheading. Just keep in mind that I only have 2 questions for this complex numbers subheading, but this is like mainly 1141 stuff, like 1141 end of the paper difficulty. So it's not for the faint-hearted. It's like the extra spicy in the Nando's range. So let's move on. Let's begin with de Moivre's theorem definition. So this is the most common definition used in complex numbers. For any real number theta and integer n, cos theta plus I sine theta, all to the power of n, is cos n theta plus I sine n theta, or equivalently in polar form, e to the I theta all to the power of n is equal to e to the I n theta. So you can think of it as kind of distributing that n inside the inputs of the trigonometric functions or inside the polar form. But just remember, whenever you use this definition, it's always important to, just write de Moivre's theorem next to the line that you're using it for. Because otherwise the marker, it won't be clear for the marker that you used de Moivre's theorem. Cool, let's move on to a worked example. Sorry. So part I says, use de Moivre's theorem to express cos 4 theta as a polynomial in cos theta. I'm going to add a blank page here. Cool. So part I is express cos 4 theta in terms of cos theta. Cool. So by de Moivre's theorem, we know that cos theta plus I sine theta all to the power of 4 is equal to cos of 4 theta plus I sine 4 theta. Now I would write de Moivre's theorem next to that, but I don't have space. But I encourage that all of you do. And using the binomial theorem, we can expand this left-hand side. This would become cos to the 4 theta plus 4i cos cube theta sine theta plus 6i squared cos squared theta sine squared theta plus 4i cubed cos theta sine cube theta plus I to the 4 sine to the 4 theta. And that's equal to, like we said before, cos 4 theta plus I sine 4 theta. And the way I did that, I just used binomial theorem and just remembered the Pascal coefficients 1, 4, 6, 4, 1. And then it becomes easy to expand. And we can group up the real terms of the left-hand side and also group up the imaginary terms, the right-hand side, on the left-hand side. So grouping up the real terms, we're going to have all the terms without the i's. So cos to the 4 theta, that's the only term without the i's. And then we can see that that 6i squared cos squared theta sine squared theta term, it has an I squared in it. And what do we know about even powers of I? Well, we can just rewrite them as real numbers. So we can rewrite that I squared as -1, and our real term becomes -6 cos squared theta sine squared theta. And if we look at our only other term with an even power of I, it's that I to the 4 sine to the 4 theta term. Well, I to the 4 we can just rewrite as 1, and we're just left with plus sine to the 4 theta. Cool, that's our real term. Now we can also do plus I and then times our imaginary term. However, it's actually not necessary in this question, because if you look at that right-hand side, we have cos 4 theta plus I sine 4 theta, and the question's asking us to express cos 4 theta in terms of cos theta. Well, cos 4 theta is just the real part of that right-hand side. So if we equate real parts, we're only concerned with the real part on that left-hand side, which we have just calculated. So after equating real parts, we're just left with this left-hand side is cos 4 theta, and we've just completely disregarded the imaginary part. And sorry, just write it in brackets equating the real parts. Cool. Now the question asks us to find cos 4 theta in terms of cos theta, or as a polynomial in terms of cos theta, which means we don't want any sine thetas in our final solution. Note that all the sine thetas we have in our left-hand side are even powers. So it's actually quite easy to convert them into cos theta. And we can use the Pythagorean identity sine squared theta is equal to 1 minus cos squared theta. And similarly, and from this, sine to the 4 theta is equal to 1 minus cos squared theta squared, because it's just sine squared theta squared, which is just 1 minus cos theta all squared. And using those two identities that we derived from the Pythagorean identity, we can simply just substitute those into this equation, and therefore we'll be left with a polynomial in terms of cos theta only. So I'm going to spare the calculations just due to time, and we end up with the polynomial cos 4 theta is equal to 8 cos squared theta minus 8 cos to the 4 theta minus 8 cos squared theta plus 1. So we get that directly after substituting in those Pythagorean identity values, where sine squared theta is 1 minus cos squared theta, and sine to the 4 theta is 1 minus cos squared theta all squared. So we're left with this we're left with this polynomial for cos 4 theta in terms of cos theta, and we're done with that question. I'm just gonna add another blank page. Cool. Let's look at part 2 now. Does anyone have any questions with part 1? All good? So part 2, hence or otherwise find the roots of that polynomial p of x. This is quite a difficult question, and it requires you to spot something as your first step. So I'm just gonna write our solution from part I. So I believe we ended up getting cos 4 theta was equal to 8 cos to the 4 8 cos to the 4 theta minus 8 cos squared theta plus 1. So that's the solution we got in part I. And in part 2, in the question, they introduced this new polynomial. P of x is equal to 128x to the 4 minus 32x squared plus 1. So I'll just write that here. Sorry, minus 32x squared plus 1. Now we're going to have to try find a link between these two polynomials. We can see that both the polynomials end with the constant term plus 1. So that's kind of hinting that there is some relationship between the two. So we're going to have to notice that this is equal to 8 times 8 times 16 cos to the 4 theta. Minus 8 times 4 cos squared theta plus 1. And we can write this as 8 times 2 cos theta all to the 4 minus 8 times 2 cos theta all squared plus 1. And sorry about that. Sorry. These are meant to be x's. Sorry about that. So x squared, 2x all to the 4, and 2x all squared. And we can already see the relationship between the two polynomials. Well, if we substitute in 2x equals cos theta, so i.e., that's just the same thing as saying x is a half cos theta. Well, then we get, for our p of x, we get p of a half cos theta is equal to 8 cos theta to the 4 minus 8 cos squared theta plus 1, which is simply just our cos 4 theta from part I. Does that make sense so far? Cool. Now, what do we know by the factor theorem in polynomial theory? So factor theorem tells us, sorry, I just keep pressing this button. Factor theorem tells us that if p of alpha equals 0, then alpha is a root. Okay, that's what factor theorem tells us. And we can use this to find the roots of our polynomial p of x. So I'm going to add in another blank page. Cool. So how can we use factor theorem to find the roots? Well, from factor theorem, if cos 4 theta, which is just our p of a half cos theta, if that equals 0, then we know by factor theorem a half cos theta is a root. That's how we use factor theorem. Okay, so essentially we're just replacing that alpha with a half cos theta. Cool. Now, let's set cos 4 theta equal to 0. Well, cos theta is equal to 0 when we have the input being an odd multiple of pi on 2. So this means that 4 theta is equal to 2n plus 1 times pi on 2 for some integer n, because we can just write an odd number as 2n plus 1, where n is an integer. And then isolating theta, we have theta is equal to 2n plus 1 times pi on 8. Cool, so we found theta. However, the polynomial p of x is a quartic, right? Which means it has 4 solutions exactly by the fundamental theorem of algebra. Whereas if we scroll down here, we actually have infinite possible values for theta, because n can be any integer. So we have to restrict theta so that we only have 4 solutions. And the way we're going to do this is, if you look at the top of this page, so where I'm putting my asterisks, we know that if cos 4 theta is equal to 0, then the r root is a half cos theta. To find all our distinct roots of the polynomial, we want to cover the whole range of cos theta. We want to cover the positive values of cos theta. We want to cover when cos theta equals 0, just in case a root's 0. And we also want to cover when cos theta is negative. So how can we do this? Does anyone have any idea what we can restrict theta to cover all the possible values of cos theta? No, that's all right. So if we restrict theta to be between 0 and pi, let's quickly just look at a graph of cos theta. If we restrict theta to be between 0 and pi, that's pi, don't we cover all of the possible values for cos theta? And therefore, we also cover all of our distinct roots for the polynomial. Okay, so we're going to restrict theta to be between 0 and pi to get all our distinct roots. And doing this, we get 0 is less than or equal to our value for theta, which is 2n plus 1 times pi on 8, which is less than or equal to pi. Now, if we multiply all 3 sides by 8, or 8 on pi, the left-hand side simply just stays as 0. The middle becomes 2n plus 1. Right-hand side becomes 8. And therefore, for our integer values for n, we get n is 0, 1, 2, or 3. And we have 4 possible values for n, and therefore we have our 4 roots for the polynomial, which suggests that we are on track because we know that the polynomial does have 4 roots. Cool. I'm going to add another blank page. So, looking at the top of that page, we said by factor theorem that if cos 4 theta equals 0, then our roots are a half cos theta. Okay, well, for n equals 0, what's our value for theta? Well, we sub it into this, and we get theta would be equal to pi on 8. And then for n equals 1, similar reasoning, 3 pi on 8, n equals 2, theta is 5 pi on 8, and for n equals 3, theta is 7 pi on 8. So just odd multiples of pi on 8, like we said before. So what does that mean for our roots? Well, I'm going to refer to it again. We said by factor theorem, if that first implication is true, then a half cos theta is our root. And therefore our roots, roots of p of x are simply just a half cos of each of those values for theta. Half cos pi on 8, half cos 3 pi on 8, half cos 5 pi on 8, and half cos 7 pi on 8. And those are our 4 roots of the polynomial for P of X. Does anyone have any questions regarding that? No? Okay. Let's move on to the next part. So then part 3 says, by examining the roots of P of X, find the exact value of sine pi and 8 times sine 3 pi and 8. So note how the inputs are pi and 8 and 3 pi and 8. And in our solution for part 2, we had like odd multiples of pi and 8. So that's kind of suggesting that we did part 2 correctly. You know, if it was asking us to find the product of like sine pi on 6 and sine 4, like 5 pi on 6, then kind of hint that we did something incorrectly. But this is a good sign. Okay, it says by examining the roots of P of X. Now, 99% of the time, that means we use the sum and products of roots. And we're trying to find the exact value of a product between two sine functions. So that's actually hinting that we use product of roots only and nothing to do with the sum of the roots. So I'm going to write here, whatever our roots are, just say our roots were alpha, beta, gamma, delta. The product of roots tells us that it's equal to the constant term divided by that leading coefficient, 1 on 128. And that's by Vieta's formula. So Vieta's formula is just another way of saying sum and products of roots, just a fancy way of saying it. And we know that the product of our roots is equal to 1 divided by 128. Cool. So I'm going to scroll down to where we found our roots, and I'm going to add another page. Okay, so we have our roots listed up at the top. And now we know that the product of all of those roots are equal to, we know that the product of all of those roots are equal to 1 divided by 128. So when we take the product of them, we're going to get a half times a half times a half times a half. That's equal to 1 on 16. And then we simply just have the products of the cos functions. And we said before that this product is equal to 1 divided by 128. Sorry. Multiply both sides by 16. We get this product, I'm just going to write it like this, is equal to 1 on 8. Okay, now we have a product of cos functions is equal to a constant, but the question is asking us to find the exact value of the product of two sine functions. So this is what the question is asking us. But we have cos functions and we need to find the product of sine functions. So does anyone have any idea on how we can, you know, like what our next step would be? No, that's all right. So a common way, or not a common way, the way you convert cos functions to sine functions, you use the complementary angle identity. So we use the fact that cos of x is equal to sine of pi on 2 minus x. Right? Does anyone have any, do you have a question? No? Oh, sorry. Okay. So this is the complementary angle identity, and this is used to convert cos functions to sine functions. You know, similarly, we could convert sine functions to cos functions. However, in this question, it's not necessary to do this. We only need this first one. And we can convert each of those cos terms we have at the top of this page into their respective sine terms. Well, cos pi on 8, using this complementary angle identity, well, that becomes sine pi on 2 minus pi on 8. And this becomes sine 3 pi on 8. Cool. I'm going to add another page. Similarly, we can actually do this for each term of cos that we have at the top. So I'm going to write, similarly, cos 3 pi on 8, using the same formula, this would become sine pi on 8. Cos 5 pi on 8, that would become sine negative pi on 8. And using the odd property of sine function, simply just negative sine of pi on 8. So we can just take that negative sign out to the front. And cos 7 pi on 8, that simply becomes sine negative 3 pi on 8. And using this odd property again, negative sine 3 pi on 8. Now when we take the product of those four cos functions you can see on the screen, and after we replace them with the sine, their respective sine values, we get sine, no. Yeah, okay, all good. Oh, no. Yeah, sine 3 pi on 8 times sine pi on 8 times negative sine pi on 8 times negative sine 3 pi on 8. Well, that's equal to 1/8 as we have from here. Oh my, that was awful. We have from that. And we have two negative signs in the product on the left-hand side. That just becomes +1. So, and we also have two sine pi on 8s. So that becomes sine squared pi on 8 times, and then 2 sine 3 pi on 8s, that becomes sine squared 3 pi on 8 equals 1/8. And we can simply just square root both sides to get sine pi on 8 times sine 3 pi on 8. Its exact value is simply 1 on root 8, which is 1 on 2 root 2, or just root 2 on 4, once we rationalize the denominator. And just note that we took the positive square root of both sides, because clearly the left-hand side, sine pi on 8 times sine 3 pi on 8, that's clearly positive, because sine pi on 8 is positive and sine 3 pi on 8 is positive. So that's why we took the positive square root of 1 on 8 as opposed to the negative square root. And therefore, we get that final answer as sine pi on 8 times sine 3 pi on 8 is root 2 on 4. Does that, anyone have any questions about that? Cool. You can see it's pretty tough question. So this would be like catered more towards the end of the 1141 paper. And here's a better written out solution that you can refer to after this presentation. Cool. And final question. This one is a little more difficult. So by considering the 7th roots of unity, find the set of non-real solutions to the equation 1 plus omega all to the 7 is equal to 1 minus omega all to the 7. Okay, well, it says by considering the 7th roots of unity. And what do we know about roots of unity? So I'm going to write at the top that for roots of unity, we have something, sorry, I'm going to use z instead of x because it's complex. We have z to the power of n. For roots of unity, it's going to be of the form 1 minus 1 I or minus I, because these four values have modulus 1. And that's the only thing we care about for roots of unity. So, but if we look at the equation we're given, there's no 1 minus 1 I or minus I on the right-hand side. So does anyone have any ideas of how we could get this 1 minus 1 I or minus I on the right-hand side? Any ideas? No? It's all good? So what we can do is we can actually divide both sides by 1 minus omega to the 7. And then we'd end up with something like this, equals 1. And we have our roots of unity standard equation. And we have to check that we can do this, because what if that right-hand side is 0? Then we obviously can't divide by that 1 minus omega to the 7. Well, the right-hand side is equal to 0, where if and only if omega is equal to 1. But let's check if omega equals 1 satisfies this equation. Well, on the left-hand side, we'd be left with 2 to the 7, and on the right-hand side, we'd be left with 0. So clearly, omega equals 1 can't be a root to this equation. which means we are actually allowed to divide by 1 minus omega to the 7, because it could never be equal to 0. So that's why we're allowed to do this, and we have our standard roots of unity equation. Cool. Now, our standard equation is of the form z to the n equals one of those 4 values. Here, our z is equal to, oh my god, our z is equal to 1 plus omega divided by 1 minus omega. So that's our z in this case. And now we're solving a standard roots of unity equation. So I'm going to add a blank page. Okay. So now we're just solving z to the 7 is equal to 1. Well, how do we usually do this for roots of unity questions? Well, we let z equal r times e to the I theta in polar form, where r is the modulus and theta is the argument. However, with roots of unity questions, our r is always equal to 1, because if we have something to an integer power being equal to something with modulus 1, then that original thing must have modulus 1. So does that make sense? We know z must have a modulus 1 if z to the 7 is equal to 1. Does that make sense? Cool. So we could actually leave out r because it's just equal to 1, and we let our z be equal to e to the I theta, where theta is the argument. Since our left-hand side is now in polar form, we want the right-hand side to be in polar form. So we write 1 is equal to e to the I of 2n pi, where n is an integer. Because if we look at the complex number diagram or the R-Gantt diagram, whatever you want to call it, then if we have the complex number 1, it lies on the real axis, and it has argument 0. It also has argument 2 pi, and similarly 4 pi, and we can also go backwards. It has argument negative 2 pi, negative 4 pi, and so on. So it's just it's just an integer multiple of 2 pi, and therefore I represented it as 1 equals e to the I, and the argument is 2n pi, where n is an integer. So now we have both sides in, sorry that I'm going a little over time, by the way. I won't be too much longer. So we have both sides in polar form. So we have z to the 7, so e to the I theta to the 7 is equal to e to the I 2n pi. And by de Moivre's theorem, we have e to the I 7 theta is equal to e to the I 2n pi. And I'd write de Moivre's theorem. Remember, you should always write this when you apply it. Cool. And now the moduli are obviously equal. I'm just going to add a page. Sorry. Oh. Okay. So blank page. So obviously the moduli are equal. So now all we're left with to do is equate the arguments. So equating arguments, we have 7 theta is equal to 2n pi. Cool. And isolating theta, we're left with theta is equal to 2n pi divided by 7. And remember, n is just any integer. Okay, cool. Now we can substitute this. We're going to leave this at the moment. So we've now solved theta. And let's go back to our original equation. So we let z equal 1 plus omega. Oh my god. We let z equal 1 plus omega divided by 1 minus omega. Okay. Now, what does this mean? I'm going to have to refer quickly. Yeah, okay. Cool.
Just go with that.
Huh?
You could just go with that if you want.
Yeah, sure, okay. So we let z equal e to the I theta, and therefore 1 plus omega divided by 1 minus omega is equal to e to the I theta. Now we can multiply both sides by 1 minus omega to get 1 plus omega is equal to e to the I theta times 1 minus omega. And now we can isolate for omega to get omega is equal to e to the I theta minus 1 divided by e to the I theta plus 1. And we have a complex number on the denominator. So usually we multiply by the conjugate of the denominator to essentially rationalize it. And obviously the conjugate of e to the I theta plus 1 is equal to e to the minus I theta plus 1. So that's why we multiply top and bottom by e to the minus theta plus 1. And expanding, we end up getting e to the 0 minus 1. So these two terms cancel out. So we're left with e to the I theta minus e to the I minus theta. And this should be a known identity. That's equal to 2i times the imaginary part. And the imaginary part's simply just sine theta. So that numerator comes down to 2i sine theta. And with the denominator, we have an e to the 0 plus 1. That becomes 2. And we have an e to the I theta plus e to the minus I theta. Should be a known identity. That's simply just 2 times the real part. And the real part is cos theta. So essentially we get 2i sine theta on the numerator and 2 plus 2 cos theta on the denominator. And divide by a common factor of 2. We get z equal to I sine theta divided by 1 plus cos theta. Our omega is I sine theta divided by 1 plus cos theta. So that's going to be our solution form. But from above, our theta we calculated was 2n pi on 7. To find all the distinct roots to the original equation of the question, sorry about that. To find all the distinct roots of this equation, we essentially want to, sorry about that. So the equation had degree 7, and by the fundamental theorem of algebra, we know that it has exactly 7 roots. So, but theta equals 2n pi on 7, clearly it has infinite values of theta. So similar to the previous question, we're going to have to restrict theta so that it has 7 values at most. And the way we're going to restrict it is we want to cover all values from 0 to 2 pi so that our sine theta can be flexible across all its range, and our cos theta can also be flexible across its range. Since we know that between 0 and 2 pi, sine theta covers its entire range or oscillation, and cos theta also covers its entire oscillation. So if we restrict theta to be between 0 and 2 pi and replace theta with 2n pi on 7, we end up getting the possible values for n to be 0, 1, 2, 3, 4, 5, or 6. And note that there's clearly 7 possible values for n, which suggests that we did it right because we know the original equation only has 7 roots. And we note that when we substitute n equals 0, we're going to get theta is equal to 0. And if we substitute theta into I sine theta divided by 1 plus cos theta, we're going to end up getting 0, or omega equals 0. However, in the question, it said find all the solutions that were non-real. And clearly 0 is a real number, which means we only care about the values from 1 to 6 for n. And therefore, our set of solutions is given of the form I sine theta divided by 1 plus cos theta, where theta is 2n pi and 7, and n spans the values 1, 2, 3, 4, 5, and 6. And that's our final answer. I know it's quite a lot. Does anyone have any questions? Yep.
So you don't have to prove that the other values will give a complex answer, or it's just inferred.
Yep. So he's asking you're asking why we only checked n equals 0 gives us a 0 solution. So omega is I sine theta divided by 1 plus cos theta, which it will always be imaginary, purely imaginary, if and only if sine theta is not equal to 0. Right? Which means we'll only get a real solution when sine theta is equal to 0. And clearly, for theta equals 2n pi and 7, that's only going to be when theta is equal to 0. Right? Cool. So that's why we only disregard the n equals 0 case and we keep the others. Yeah, but that's a good question. Does anyone have any other questions? Cool. Yeah. Yeah, that's it. Yeah, and then next is calculus tomorrow.
Awesome. Thanks.
Thank you.
Awesome. Just if you have any other questions, like something on the slides, just contact MathSoc. They have an email, or just I can give you any of mine. We can give you our phone numbers if that helps. But apart from that, all the best for your exam.
Yeah.
That pretty much covers everything. So I know like online MATH1131 and 4.1 exams are notoriously difficult. But as long as you just use some of like your fundamental identities, especially around complex numbers and like matrices, determinants, you should be just fine. And I think it is semi-open book, so Simple Lab.
Semi.
Is it?
It's fully open.
Fully open book, yeah.
Fully open.
Simple Lab to the rescue, so yeah.
Yeah.
Anyway,
Cool. Thank
go
you all
ahead.
for coming.
Yeah.
Are the slides going to be uploaded anywhere?
Yeah.
Yeah.
Where?
Let me stop the stream.
Yeah, sure.
MathSoc website.
MathSoc website.